get that balloon, I will show you the gluten balloons.
Rising of Bread by Anna, Yanchi, Vishal and Tracy. Today we will be exploring two concepts, yeast respiration and the formation of gluten complexes and both their roles in the rising of bread.
So how does bread rise? Kneading, proofing, and baking are the three main processes required in order to make bread. In the kneading process, water is initially added to flour, causes the hydration of gliadin and glutenin proteins, and leads to the formations of gluten. Gluten is a water-insoluble protein. Two of the naturally occurring proteins in flour are called glutenin and gliadin. Prior to kneading, gliadin and glutenin remain separate on a molecular level. When sufficient water is added to dry flour, the two proteins emerge from a frozen state and become flexible and able to move about. It is not too different from stiff, dry spaghetti becoming flexible when it is cooked in water. The process is called hydration. As water and flour are mixed, the hydrated proteins are brought together and begin to interact. They literally begin to stick to each other through the formations of chemical bonds. These new chemical bonds are called crosslinks. Again, it's not like a pot of cooked spaghetti that has been poured into a colander and allowed to drain. After a few minutes, the strands of spaghetti stick together unless they are separated by the additions of a little oil. In gluten, there are different chemical bonds such as disulfide bonds, hydrogen bonds, and ionic bonds.
To prepare the gluten balloon, combine 2.5 cups of flour and 3/4 cups of water. Slowly add the water as you combine the flour together. Ensure that the water is well incorporated with the flour, as too little water will not allow hydration to occur and gluten to form. Next, knead the dough by pushing it forward with the heels of your palms, repeating the process until the dough becomes stretchy.
The kneading process stretches the gluten complexes. Stress induced by mixing breaks bonds between the protein chains, allowing the chains to move and become realigned. The new bonds that formed allow relaxation of the dough. Continued mixing causes more crosslinks to form between the proteins until a large network of chemically linked proteins is formed. When dough is mixed or kneaded, the hydrated flexible proteins are stretched and aligned in the direction of kneading, providing more opportunities to form crosslinks between the proteins. Kneading also incorporates air, which helps to form strong disulfide bonds. As kneading continues, the protein networks combine to form sheets of proteins.
Here are some scanning electron micrographs that show the protein network. The first one shows the protein network formed after water is added to flour with no mixing. The second one shows how the protein strands begin to stretch and bond together after a few seconds of kneading. Next, we rinse the starch out of the dough ball such that only gluten is left. The first image shows gluten with the starch granules trapped within its protein matrix, while the second one shows gluten with all the starch rinsed away.
To show this, we conducted an iodine test on the dough ball and the gluten ball. As you can see, the iodine on the dough ball turned blue-black, meaning that it still has starch, while the iodine on the gluten ball remained yellowish-brown, meaning that it no longer contains any starch.
Gluten, formed by the chemical cross-linking of glutenin and gliadin, is a very elastic substance. Neither protein alone is as elastic and stretchable as gluten, but when chemically linked together, the new protein becomes elastic and stretchable like a rubber balloon. Like a balloon, gluten can be inflated with gas and steam as dough rises and bread is baked in the oven. As bread bakes, the inflated gluten dries, turning into a strong but flexible structure that creates the holes in chewy bread.
Air is incorporated at the proofing stage. At the proofing stage, breakdown and fermentation occur. As bread dough ferments and proofs, the yeast begins to feed on the sugar in the mixture and produces alcohol and carbon dioxide gas, which is what causes the gluten network to expand. This leaves an open cellular structure with the gases trapped in the pockets.
To simulate the gas during fermentation, we pumped air into the gluten ball, forming a gluten balloon.
Dad, look at what my gluten balloon can do!